Ever wondered how we predict the weather? With surprising accuracy, design a soaring skyscrapers that define our cities, or understand the intricate dance of a rocket launching into space? The answer, in so many of these marvels, lies in the powerful language of calculus.
At its heart, calculus is the mathematics of change. Think about it. The speed at which a car accelerates, the rate at which a disease spreads through a population, or even the subtle curve of a bridge designed to withstand immense forces. Calculus gives us the tools to precisely describe, analyze, and predict these dynamic processes.
Calculus is a branch of mathematics that studies change through the concepts of limits, which describe the behavior of functions as they approach a certain value. Derivatives, on the other hand, measure the rate of change of a function. And finally, integrals, which represent the accumulation of the sum of all quantities under a curve.
Integrals are a key idea in calculus that help us measure things that are constantly changing. Instead of adding big chunks, integrals add up tiny pieces to find a total, like the area under a curve or the total amount of something over time. They are basically tools that help us understand how small changes build up to create something bigger. In real life, integrals are very useful. In physics, they are used to find the total distance a car travels when its speed keeps changing. In economics, integrals help us calculate the total profit or cost when production varies. Integrals may seem complex, but they simply help us add up things we can't measure directly.
You can change the letters depending on the context. All common derivative rules, polynomials, exponentials, etc. come from the same limit definition, except piecewise function which need special care. When we differentiate a function, we usually get its general derivative form. When we take the derivative of the function, we usually get its general derivative form. Unless we substitute a specific value of x, we get the exact slope of the tangent line f of x at that point x, or the instantaneous rate of change at f over x. For example, suppose a block of ice is melting. Let the mass in grams be f over x at time x minutes be f of x equals 500 minus 4x. If we take the derivative, it means the ice loses at a constant rate of 4 grams per minute.
This example is the same thing we want to do with functions, where we take the limit of the function we are describing where are they going. Let's see an example of this with the function f of x equals 3x squared minus 1. For this function, I'm really curious what value the function is approaching as I use x values close to number 2. Let's see this by using some inputs 1.9, 1.99, and 1.999. When I use this, I get values such as 9.83, 10.8803, and 10.988003. From these values, it appears that the function is approaching 11. So we can say the function as x approaches 2 is 11. Remember, what I'm really saying here is that we can get arbitrarily close to the number.
In the end, calculus isn't just something we study. It's a way of understanding how the world works. From small changes in nature to big innovations made by people. Calculus help us see patterns, movements, and growth. And as we keep learning, we realize that these ideas don't just solve. They open our minds to new possibilities.